methods.
Okay. Okay. Thank you. All right. So shall I start?
You can start with this. Yeah. So next speaker is Sinha. We will talk about BanditQ, Bandits with BanditQ.
Okay. All right. Thanks everyone for coming to this talk. And this is fairly an ongoing work, so feel free to stop me if you have any questions or comments. So we'll be talking about a variant of the bandit problem with some certain constraints, the fairness constraint. And since it's actually a student, student event, so I thought about something that describing the problem is something that students can relate to. So here is this problem. So let's say there is a prototypical professor and who receives research grants over time, right? So as time comes, he receives some research grants, and he, with each research grant, he actually, comes with some problems, and he has got n PhD students. So he wants to distribute these problems to his n PhD students. So he can only, assign one problem to one of the students. And so what he wants to assign them fairly in certain sense. So that I'm going to describe like what fairly means in this sense. Right? And is it fine?
Yes.
Okay. All right. So he wants to assign to them fairly, right? So that So now let's describe what fair means. And so here's the setup. The setup is that these are like new PhD students. So the professor doesn't have any idea like what are their problem solving skills, right? So he assigns one of the problem to one of his students, and after some time the student actually solves the problem or he doesn't solve the problem. So let's say there is like some inherent probabilities, like there are n PhD students, and the probability that this ith PhD student solves the assigned problem is pi, and pi is unknown to the professor. So you can only just estimate these things as time goes by, right? From his experiences, right? So the skill levels of the students are initially unknown to the professor. It can only be learned through past performance. All right, and right. Okay. Right. And okay. So here is the students remain in the school for T years. Right. This is their PhD duration, and there are certain degree requirements. So the degree requirement is that the student needs to solve the problems at a minimum rate. So lambda I problems per year. So the ith students need to solve lambda I problems per year. It's a long-term effort, and this concept has to be met. And these minimum requirements are not to be feasible. So this department is like not super good, and he knows that the students can actually solve the problems at this rate. So this this rate is feasible. It is known a priori. And so what is the advisor's problem? So advisor's problem is that he wants to solve as many problems. Of course, he wants to get as many as publications possible, and subject to each of his students meeting the minimum requirement, so that none of the students gets kicked out. Right. So this is the problem, right? Of course, this is a fun problem, and we see that this is like a very much relevant problem to the real world. For example, this has got data applications, recommendation systems, online ad allocations, crowdsourcing, wireless scheduling, etc. But so this is the basic problem that you will be focusing on. This.
The regret minimization problem.
Yeah, so we will come to this. Yeah. Yes. So we will be describing. This is just the story, just get you motivated. But yeah,
it is not a fun problem.
Really, it's fun for them. Right. So the question is, so what is an optimal problem assignment strategy for the process? Right. So now, okay, so the story is over now. So now let's formalize this. So we are given a set of A norms. So you can think each of the students as one of the A norms, and a target reward vector lambda. Right? Lambda is some non-negative reward vector. The lambda could be 0, and this will be a special case, and we will see that what it actually means. So on round T, the online policy, the professor has a policy. It sets one of these arms, let's call it IT, to play. Just define the problem. So both the policy and the selected arm IT receives an IIT reward value of RIT, right? So it could be like whether this could be 0 and 1, binary, whether the problem has been solved or not, or it could be some number. I mean, probably the quality of the solution or something like that. And so what is the goal of the policy? The goal of the policy is to maximize the rewards, the total cumulative rewards accumulated over T rounds, right? While ensuring the long-term reward accrual rate of each of the rounds, which is lambda I, this is met, right? So this problem is interesting in both full information and bandit feedback settings, and I'm going to describe like what it means. Full information means, so at the end of each round, the professor gets to see the reward that he's opted. So for example, let's say the professor assigned the problem according to some distribution xt. So at the end of this round, this entire reward vector is revealed to the professor, and he sees, okay, so this student has solved the problem, this problem was solved. So this is a full information setting. The entire reward vector, there is RIT, it is revealed. And in the bandit feedback settings, only, so let's say the professor assigns a problem to student I, then only the performance of that student I is revealed. So no other non-causal information is revealed. So of course, this full information setting is kind of much easier to work with, but we will solve this problem. We will see that this kind of, these two settings are kind of equivalent. I mean, the same sort of analysis goes through. And so initially we'll be focusing on the full information setting, and then later we'll move on to the bandit setting, right? So any question on the setup? Yeah.
What is long-term reward?
Long-term reward will be formalized in the next slide. In the next slide, I will just give a formula. Then, yeah.
So one question for you.
Yeah.
This long-term constraint, if you don't have a finite time constraint.
Yes.
You will have.
We'll come to that. Yeah. So everything will be finite times. We'll be proving regret bound with finite time regret bounds. So this is actually formalized in the next slide. So yeah.
At any point of time, the regulator will query RF student to get the.
Yes. So you make some assignment, right? You make some assignment, then you get to see the entire reward vector, either the entire reward vector that is RIT or only the component of the assigned problem, right? So of course, I mean, you get to see in reality, you only get to see the performance of the student, right? Not any non-causal information that you have not done, but I mean, theoretically, both these settings are interesting, right? And we'll solve this thing in both the settings. All right. So any question so far? Okay. So let me now formalize what it actually means and what is the performance metric. All right. So now let mu denote. So mu is the unknown vector. That's the expected reward obtained. So these are the PI. So you can think of the mu to the PI. That's the expected, the probability that each student solve the problem. It's a latent variable. It is not. It is unknown to initially unknown, and this has to be learned sequentially. And let's say xt is a policy. It actually assigns. I mean, this could be a probability distribution, right? If it's a probability distribution, so in general, it could be some vector in a feasible set, right? So xt is the action, and it denotes sampling probabilities from round, right? And now this omega lambda, it denotes a set of all static feasible distributions. So this is the set of distributions against whom this policy needs to compete. Okay, so what are the properties that are required? First of all, this vectors in omega lambda, it needs to satisfy the long-term reward constraints, right? And now since it remains static, so this x star is not changing over time. So it simply means that this xi star times mu I must be greater than or equal to lambda, because I need to meet the long-term reward constraint, right? And of course, if it's a property distribution, so it satisfies the other two constraints that each component of x star is non-zero, and I mean greater than or equal to 0, and the sum of this xi star equal to 1. So this is the the competitor set, right? The policy needs to compete against this set, any vector in this set, right? And what do you mean by competition? So I'm going to prove that there are two different metrics that I would like to have bound on. The first is regret metric. So let me parse this for you. So the regret metric is the difference in reward obtained by the best static distribution in hindsight. Right? So this is the first term. There is x star times mu. This is the expected reward obtained by this vector x star over this entire time horizon t. And since it doesn't change with time, so it is simply x star times mu. This is the inner product times t. Right? So this is the benchmark. And this is the second term denotes the performance of the policy. So let me parse this. So the expectation is with respect to the randomness of the policy. And this RIT times the indicator of IT. So you get a reward of RIT at time t. If and only if the policy actually selects the error. So that is the indicated IT is at your I, and you sum this up, right? So this is the total reward over horizon of length t, accrued by the policy, and this is the reward obtained by the benchmark. Right? So this is a regret metric with respect to this X star. And so this is, and I would like to have this quantity to be sublinear, right? So this is like one of the goals. And the second goal is that this policy needs to be feasible in the sense it needs to accrue reward. You need to get the reward at the rate of lambda, right? So in the long term, this means that let's say I just considered a very long time horizon. So this is 1 over t is the rate, and this is the expected total reward obtained in time horizon of t. I want in the limit it needs to be greater than or equal to lambda. But this is again, it is a like long-term metric, so I don't really like to take limits. So what I'll be considering, I'll be considering a finite time metric. So this is even much more stricter than this one. So this is called the degree of violation, right? So this degree of violation is the expected, the difference in the expected difference between the target amount of problems that student needs to solve minus the actual number of problems that the student has solved, right? So this is the first term is simply the target. This the sum of lambda I, and this is the expected number of problems student I has solved. And I'm taking the worst case violation over all of this. So what my objective is to get derive a policy for which both this regret t of x star it is sublinear, and this v of t is also sublinear. Yeah.
So the policy that you're designing is aware of what sort of time horizon you're looking at.
So right now, yeah. So you can assume that only the capital T is known, but this can also there is a trick called the doubling trick. So it is actually not needed. But right now, for simplicity, you can assume that this total time horizon, this T, that is duration of the program is it's 5 years. Okay. All right. All right. So okay. So let's continue. So now I would like to. So I mean, I think most of you have heard of this term, stochastic bandit. It is the most canonical setting in the bandit. And now I'm going to compare our problem with this canonical bandit problem, and we'll see like where the difference actually lies. Right. So what happens? Just to recap. So what happens? The multi-arm bandit, the stochastic bandit, there is a set of n arms, and the policy pulls only one arm at a time. Right, and there is a reward vector associated with each of these arms at any given time t. Let's say they are IID, and there is an unknown mean associated for the ith arm. Right, so the objective of the classical bandit problem is to design a policy. Right, that's the arm pooling policy. So that is regret metric. Right, the only regret, the pseudo regret metric. Let's say this the maximum reward obtained by any of these arms. So this is the max of p1 is the base term in hindsight, and this is the total reward obtained in time by the base term. I mean, had I knew this, what is the base term is, I always pull the term. So this is the expected reward that I'm going to get, and this is the reward obtained by the policy. So the classical bandit policy, they want to design a policy for which this regret T is sublinear, right? And now let's see. So how our problem fits into this framework. So there is the main difference. The main difference is that this is the standard MAB problem. What they want to do, they want to identify what is the base term, and they want just prove that base term as many times as possible. So this arm identification happens through some exploitation versus exploitation, and this is what the standard MAB does. Right? There is no fairness metric. There is no constant that needs to be satisfied. So compared to this, so our strategy, this standard bandit problem doesn't of course work in this setting, because maximizing the rewards per round is not the correct objective here, right? So I'm not competing against the best term. So what I am going to do, I'm going to compete against the best distribution of arms that satisfy the reward constraints, right? So instead of competing against the best term, I'm actually competing against a distribution of arms, and this is the right objective, right? But you can see that if I set lambda equal to 0, so there is no constraint on the rewards. This is the same problem. Right, so our problem is strictly harder than the MAB problem, the stochastic MAB problem.
Your problem, when you put an arm, rewards are still stochastic.
The rewards are still stochastic. Yeah, so there is no adversarial. So I'll come to the adversarial setup a little bit later. So I'll introduce it, but right now it is only stochastic.
Now, if your constraint was not in the limit, but maybe you said, okay, your regret should always be bounded.
Yeah, so actually, yeah, so actually, yeah, so what I actually want, so this is the violation metric. So I'm actually looking at a finite time metric. So this is a degree of violation.
No, but suppose the constraint is that this violation should always be bounded. Would that be
it is very difficult to prove. I mean, it's actually impossible to show that it's actually bounded by a constant. So what you can actually hope for is a sublinear in time.
You can't design strategies where you see that the violation becomes large, can start living correctly.
Then it will be hard to do your regret metric, right? So you need to make a balance between the regret and the violation, right? So yeah, so that's the thing. So we need both the regret and violation to be as small as possible, but preferably possibly they're doing sublinear fashion with respect to time, right? All right. So okay, so what is our main result? I'm probably running a little behind time, but anyway. So our main result is a black box reduction of this problem to this adversarial multi-bandit problem, right? So this is a stochastic problem, but I'm reducing this problem to an adversarial version of this multi-bandit, where the rewards are actually not selected. I mean, it need not be IID stochastic. It could be adversarial. This policy simultaneously achieves T to the power 3/4 regret bound for regret bound as well as violation penalty. So this is our main result. So we have lower bound. So there is a trivial lower bound of square root t for both, right? And so this is a very recent result. So this is possibly, I mean, probably achievable, but I'm not going to describe it here, right? It needs a little bit much more careful analysis. But this one is kind of easy to do, and this is what I'm actually going to describe next. But this is just a kind of extension, right? All right. So here's the idea. The idea is very different from the normal stochastic multi-bandit problem. Let's say KLUCB and that sort of thing. And our idea, actually, our algorithm proceeds have very different analysis, or the algorithmic ideas are also very different. So what I actually do, we actually keep track of the violation using a recursion. This is called a queuing recursion. So QIT is for each RMI, I define a random process. It's called defined by QIT, and this process evolves like this. So let me parse this for you. So QI of t is simply the previous one, the QIT minus 1 plus lambda I. So this is the target rate at which this arms needs to be pulled. And this is minus of RIT times XIT. So this is the expected rate for the round T, given that we have already selected your decisions, that is XIT, right? So for now, it might look certain arbitrary, but let me just intuitively argue like why it could be the right kind of thing to look at. Because you can think of this, let's say this is just keeping track of the degree of violation, the constant rate of violation that you have acted up to time t, right? So this lambda I is the target rate. So at time t, you need to pull the sum lambda I times t times, right? But your policy, which is kind of learning as well as pulling, exploring versus exploiting, it has only pulled this thing summation over RIT times XIT times. So this is the difference. This is the kind of thing that you're falling behind in your target rate. So this QI keeps track of this backlog, right? What is XIT? XIT is the policy, right? The distribution that is used at time t for selecting the arms. It's a probability distribution. It's a probability mixed with the policy at time t. And XIT is simply the ith component of that.
And to get RIT, don't you need the defined in the bandits, right?
Yeah, we'll come to this is a full function setting. So we assume that, yeah, I'll come to the bandit setting later. This needs a very minor change. Right. So here in the full function setting, the entire RIT is revealed to you after you have selected here revealed XIT. So this is well-defined recursion. So you can do that, and now we will see that how to modify this thing to the bandit setup. All right. So what is now? Okay. So what do we want to do? So we want to stabilize these queues. So in the kind of queuing theory literature, I don't want my queues to blow up, because if the queues blow up, then it means that I am falling behind my target rates. So I need a policy that can also stabilize the queues, apart from having a sublinear regret bound, right? So we need to make this balance, and this is how this balancing thing can be worked out. So I define a new reward function, Ri dash of t, right? This Ri dash t consists of two parts. So the first part is QIT minus 1. This is simply the backlog in your queue, and plus V. V is a constant, which is said to be square root of capital T, which is the entire horizontal length, times RIT. So this is your new reward vector. So I'm going to feed this reward vector to an adversarial map policy, right? And this is how I'm going to select my XIT. That is the probability distribution that is used for selecting the arms at time. And so how it actually works out, what is the actual policy? It's simply the online rating ascent policy. But interesting, you can look at there is no learning rate as such. The entire learning rate is it is totally causal fashion. It is derived in a total causal fashion. There is no parameter that I'm going to adjust it here, right? And this is very important because this kind of policies, this is known as the second order regret bound. It gives a regret of the form norm of Ri dash of t whole square. Now you will see that this regret bound, I mean, there is a little difficulty in this analysis because Ri dash t itself, it depends on Qi of t, right? So the policy affects QIT, and this in turn affects the policy the next round. So this actually goes in a lockstep fashion. So the question is whether you can show that I mean this is doing the right kind of thing, because there is in the regret bound there is also this unknown QIT over there, right? So this is where a new kind of analysis is required. So let me first tell me what are the main analytical challenges involved compared to the normal bandit analysis. The rewards are, first of all, the rewards are no longer IID because QIT is definitely something that has got memory. So we can't just use any stochastic MAB problem. So this is the first thing, that it is a presence of this QT variables. The rewards are no longer bounded. Although I assumed this RIT to be between 0 to 1, this Ri dash of t it involves QT, which I don't have any control over. And QT is kind of growing sublinearly with time, right? So this is like the second obstacle that I need to overcome in analysis. And third is that their interdependency of this QT and the policy. So one is affecting the other, right? So this is why it requires a very new kind of analysis. And fortunately, this is okay. So this is the new kind of analysis that we're proposing. So, yeah.
So typically in Bandits, you just have to separate out, you want to find out this is the best analysis.
Yeah.
But now I think what's going on is you have to learn the rate lambda I.
You have to know lambda is given to you. Lambda is given to you. Lambda is the target rate. This is the rate that you would like to.
But you have to make sure that you're matching the target rate. Right?
Yeah, exactly. The policy needs to make sure that it is matching the target rate.
I think somehow that makes it the root key regret.
Yes. So the root key regret is there even if you make lambda equal to 0, you can't do better than square root key in terms of regret.
So lambda I is for each PhD student you have a given lambda.
Yes. I'm given a target rate lambda, which is given at the beginning of the school year.
So why not just but then it's something that it should not be that much of regret, right? Because so
let's say I said lambda equal to 0.
See, you make sure everybody gets lambda IT ratio.
Yeah.
And now you have enough, you learn what they are going to give enough samples, then you know
right.
You can rest to the best guy.
Yes. So the thing is that meeting only lambda is not enough, because you also need to get the regret, and regret is defined. So you have to compete against all distributions that satisfies this rate. Right. So for example, let me explain. So let's say lambda is equal to 0. There is no target rate. Right. So then, I mean, this QT constant, this kind of becomes trivial. Right. So then you are actually competing against the best target. This is the policy. There is a special case of the policy. Right. But if you have some non-trivial, non-zero lambda I, it is not only it is not enough for you just to meet the rates, because the regret metric defines it's a distribution. It has to compete against the best distribution satisfying the rates. So that is why you can't avoid the square root. So potentially one can do T2 better than T2 over 3/4, and we will see that. But square root T is definitely a hard load one for this problem.
We are very aware of the regret model one.
Yeah, right. So there is I mean, it's solely coming from the fact that you are competing against a base distribution meeting the lambda. For example, this lambda is pretty very small, right? I mean, for which this is the optimal policy anyway meets the target rate. Then this problem becomes kind of trivial, but you don't know applied. It depends on the distribution. Yes, any question?
That's right. I think I need to know.
All right. So this is okay. So now the analysis is first to define a potential. It is a potential list analysis. To define a potential function, which is a sum of the squares, and then using the dynamics and the policy, the regret bound, you get an inequality. This is called the self-bounding inequality. And you see that this inequality is very interesting in the sense it has got unknown in both the left hand side and the right hand side. And not only that, there is a sum. There is a nonlinear, and there is a sum on the left hand side, on the right hand side. So you need to solve this sort of inequalities. And in control theory, this sort of inequality is known as difference inequality. A special version of it is solved using something called Grunwald's inequality in continuous time. And we'll be seeing that it is actually applicable here in this case as well. So this is the analysis is not generally not there in Bandits. So we have to develop this analysis from scratch. And the step 3 that once you solve this sort of recursive inequality, show that if this special choice of t, which is I just put theta square root of t, this gives expression of QIT. This grows sublinearly. This is t to the power 3 by 4. Not only that, the regret is also sublinear t to the power 3. So as Sandeep mentioned, definitely there is a scope that we know the hardbound to the square root of t. We can potentially do better, and indeed we see that indeed this is an ongoing work, and we are seeing that this is the case. One can do better in this case. All right.
Let's discuss how this root no longer the key.
Yeah. So root algorithm is
what's the algorithm for it?
So let's say all lambda equal to 6. Then it is a normal the bandit problem, stochastic bandit problem, and I want a problem independent lower bound. And for problem independent, yes, that doesn't depend on the. Yeah, so it's not log
This is not instance specific.
This is not instance specific. This is the problem.
I'm saying instance specific.
Yes. No, I'm only looking at the right now the problem independent lower bound. So that is where the square root is coming. Okay. All right. And okay, and as Sandeep said, so this is t to the power 3 by 4. Whether you can actually make it square root of t. So what we could actually prove the average of regret. If you take the regret about all the time horizon, take the average. It is actually like square root of t, which is kind of encouraging because it kind of hints that the actual order of growth of regret is actually square root instead of t to the power 3 by 4. But it requires a little bit more thought than just proving this hard square root bound. But this is a kind of encouraging result. And now let's say I'm considering the other extreme. I don't care about the regret at all. I only care about meeting the constraints, right? The rate constraints. Then you can actually show that expectation of QIT is actually square root of t. So this is again the special case. So this is kind of encouraging results, and it says that probably we can actually improve the bound from t to the power 3 by 4 to square root t, and this is indeed the case. And but this is a very recent result, and I'm not going to discuss it here. And okay, and now to answer one's question. So what happens in the bandit feedback setting? So previously, as if that I know all this the internet identity, but in bandit feedback you only get to see the component of this the selected component, right? So you just slightly modify the queuing recursion. So instead of using a small of xit, you just use capital of xit. And what is capital of xit? It is simply the indicator vector. Right? It is either 0 and 1. And so again, this makes sense because it only involves the RIT for this thing, and we show that this is enough. The same analysis goes through. And
we don't pull the arm, it goes up and down.
Yes, exactly. Right? Otherwise, it just goes down by minus RIT. But for the bandit case, the analysis is a little bit more complicated because in addition to the square root of this R dash of t square term, you also have another max over rewards. This term is there. So it requires a little bit of more careful analysis. It really needs a Martin-based analysis, but this can be done. This is already there in our paper. And this is again, we are getting the same sort of regret form and violation penalty. T to the power 3 by 4. The constants are a little different. This is n is the number of forms you have. It's a little worse than what we had for the previous case. That's the full information feedback. But in terms of the growth, order of growth, this is the same, right? But it requires a little bit more careful Martin-based analysis. So this is my kind of last slide. I'm almost done. And so this is like a very recent work. So previously I was only looking at the long-term constraints, right? So we have to meet this constant over the horizon. What if you have instantaneous constraint? So this is, and let's say there is no stochasticity. So this is online convex optimization what you have, but at every time, in addition to a cost function, you're also seeing a constant function GT of x, and there is no stochasticity. GT of x is also decided by an adversary, right? It's a very hard setup, and the question is whether you can say something intelligent about this setup as well. And we actually show that. So previously, this problem was conjectured to be impossible to solve in the literature, right? And for some reason, but we actually we have found a policy that gives you t to the power 3 by 4 and order of t to the power 3 by 4 both the violation penalty and the regret in exactly the same setup without any assumption. And if you make more assumption, you can actually reduce this bound both to square root of t and square root of t. It's a very recent result. So if you get stayed, you can actually discuss this later. Yeah. So as I said, the better bounds are possible with more assumptions and structure. For example, strong context helps in this sense. Okay. So these are some simulation results for this the BanditQ policy. You can say, let's say there are two arms, and this target rate, the one is shown in blue horizontal line, and then red horizontal line, and you see that this policy very nicely meets the target rate. This is a Q. This is how this Q evolves. It's kind of, it oscillates, but it's kind of stabilizes. And regret is very interesting. It is negative, so this policy is actually doing very good. But it is probably need to set up. I mean, this particular the lambdas and uis that you showed, but it actually expected to grow. It cannot be more than square root of t. This is the full information setup. The same story repeats in the Bandit setup, but you have the queues. It becomes much more detailed because you have less information. So the open problem. So the question is again just to repeat some of these question: are the regret and constant violation rates achieved by this policy? These are optimal. Can we actually do this? So this is a like ongoing investigation. How to extend this algorithm to a much more challenging bandit context optimization setup, where you have again the online context optimization, but you're only given access to the value of the safety and G, nothing else, no gradient information, right? And the third thing is that whether we can actually, this is all about, this total regret function is separable over time, sum of the cost over time. But if it is not a sum, it's not separable, it's some, some concave utility function you have. So again, so we had a very recent series of work on this concave utility, and there we showed that it is indeed possible to get sublinear regret. The question is whether you can actually, do the same thing with constraints as well. So these are the two studies. So if you're interested, these two papers are on archive, and if you're interested, you can take a look at this. So with this, I'd like to conclude my talk. Thank you. Any questions?
Yeah, so why don't you do the extent-based setting as well?
Now?
No.
So it is there. We can discuss it in my office. Yeah, so it's a kind of very interesting.
For elements, for instance.
Yeah, instance-based and. Right. I mean, so this is actually kind of ongoing work with Rahul. We have been working on this problem, and the kind of analysis that we had, I mean, it requires combining things from control theory, for example, nonlinear optimization, nonlinear control, grown walls in liquid and stuff. I mean, this is kind of very unexpected, because this kind of things are not there. I mean, it's not used in this sort of literature. And so the results are kind of very surprising and very interesting as well. Yeah, but this is kind of the teaser that I can only give you. I don't have the slides here. Sorry for that, but we can definitely discuss. Yeah, the instance, simply without stochasticity, when you have only constant online context optimization with instant eating as constant, this problem, it's a very interesting problem, and yeah, I'll be happy to discuss. Yeah, more questions on this. All right. Thank you.
We get that now we are going for lunch. No, yeah. Another guest.